So I will talk a little bit about lazy sequences and maybe wait a little bit. So lazy sequences are one of the core parts you will encounter in Clojure. There's a huge library in core to work with sequences, and it's an interesting historic. There's an interesting historic story behind lazy sequences, how they developed, and why they are the way they are today. And so I will take you a little bit on a time travel into the past, see where does it begin, and how did it develop into the form we know today. So, who in the audience remembers lazy cons? Still a few. Okay, so when we go back, and as each fairy tale, this one also starts once upon a time. In the beginning, there was a cons cell. So it was the basic linked list. You have a two-element structure with one first element and one reference to the next elements in the list. And then at the end, there was nil. That meant that the list was basically exhausted. From this concrete structure, as it is known from the Lisps, like common Lisp, one can basically extract some kind of definition for an interface. So a sequence is either a thing which has a first element and a sequence of remaining elements in the sequence, or it is nil. That was the initial definition for a sequence. And it basically means that there's also no empty sequence. So empty sequence means it's nil, there's nothing there. As soon as you have something, it has a first element. So we can use cons to build our sequence. This is not much different from the list example. So we have a cons A and cons it onto a second cons, which is a nil, a B cons onto a nil. And this gives us our list. But the point is, we construct it basically from right to the left. We start at the tail and cons onto the head of the tail and consume it from the other way. So we start on the left and consume it to the right. Now the question is, why do we have to know the tail at construction time? Though in this example with the cons, we have to first create the second cons to be able to cons this A on it. And the question is, why do we have to? We could also have a kind of delayed computation to get this tail. And this is basically what lazy cons does. Lazy cons also constructs a sequence. You have a first element, the A, and you have a sequence of remaining elements, which is in this case only a B. But the computation of this sequence of remaining elements is deferred until you really need it. And okay, in this case, it's not really exciting. So let's have a more meaningful example. We can define a function numbers, which takes an integer and basically just creates a lazy cons with this integer as a first element, and then recursively calls itself with the integer increased by 1. If lazy cons would calculate the tail immediately, you would have a recursive loop here, and since we don't have a base case which terminates this loop, we would just recurse infinitely far until we get a stack overflow. But due to the fact that the computation of this tail is delayed until we really need it, we can basically create an infinite list. So when we say number 0, and then we get all the numbers from 0 on, and if you don't agree that 0 is a natural number, we can also start at 1. And this is really an infinite sequence. As long as we don't want to print it, this will work fine because it's not realized in the memory. It's just some promise that if we ask for further elements, we will get it. Though this has some nice nice attributes, this style of coding. We get this elegant recursive style. We can write normal code in a recursive way without getting this Stack Overflow issue. But due to this delaying of this computation, we have to mind the dynamic context. Though it's a typical problem almost every beginner runs into. You have a binding, and you create in this binding, which is set up, a lazy sequence and pass it out. And then someone outside starts to realize the sequence, then the binding is gone because it's not in this dynamic context anymore. So you will get an error. So you have to either realize the sequence inside the binding, or you have to keep the sequence all the way inside the binding. Another issue is that we should not pile the heads. This basically happens every time we use a sequence. When we have a sequence, we add a filter on it, and we add a map on this filtered elements. And this is piling sequence on top of sequence. And if we do that too much, we basically run into the same issue with the Stack Overflow, because when we realize the first element, it has to realize the first element of this inner sequence, and it propagates through. We get a cascade of first calls, and in the end, we get a Stack Overflow. In normal code, this almost never happens, but it can if you basically have, for example, a loop going through some data, and you recurse on concat and concat and concat, or on filter, filter, filter for various predicates that you extract from somewhere else. And if this somewhere else is not bounded in some way, you can easily get into this situation. Also, since the computation of the elements is not realized immediately, we can have a very memory efficient way of working with large data, with large sequences. And in fact, numbers returns a potentially infinite sequence. So if you have enough time, you can just run and count how many natural numbers are there. And there's just one thing to keep in mind: don't hold the head. When we keep a reference to the head of the sequence, then we keep also reference to all the realized elements. And this builds up, and then suddenly you get a memory problem. And this is also a non-trivial problem. In the beginning, there were even issues inside Clojure where innocent-looking code basically retained the head of the sequence, and you got a problem and didn't know why. So there were special measures taken in Clojure to avoid the situation. So when you work with large sequence, you take the first element, process it, throw it away, take the remaining, and don't keep a reference to the head of the list. So this is a very nice properties which we can use in our programs. So let's see how we can actually get hold of sequences, or what a sequence actually is. So what is a sequence? The trivial examples of what const and lazy const return is by definition a sequence, because they are the constructors for this non-empty case. Empty would be nil. So what about a list? Is a list a sequence? It seems so. There is a first element, we have 1, and we have remaining elements, 2 and 3. But what about the empty list? Is this a sequence? It has no first element, and it's not nil, so it doesn't fit into the description. But we could turn it into a sequence if we take a function seq, which gives us a sequence on the empty list. It would return nil. So we have to ask the question again: what is a sequence in a different way? Up to now we talked about what is technical view, or what is behind this, the lazy sequence, but there's also the question: what does it mean? How do we interpret what a sequence is? And it can be seen as a sequential view on a collection. And yeah, it's not a collection on itself. It's more like when you have an iterator. It's also not a collection, but it's a pointer somewhere in your data structure, and you can walk through it. Sequences are similar, but without the mutation. When you have an iterator and you ask for the next element, the first is gone. You cannot reverse with the same iterator the collection twice. You have to create a new one. Sequences don't do this. They cache the intermediate results. So if you keep the head of the list, you can traverse it as many times as you like. And this view on this collection, on a collection, gives us a very nice way to run computations on the elements of this collection, because it's independent of the actual form. You can ask the collection, give me a sequence on your elements, and then you can use all the tools you already know and which are in the sequence library in the core to work on the elements without knowing where they come from. Was it a vector? Was it a set? Who cares? So we have basically a new thing, a seekable. It's a thing which we can use through a sequence. So a seekable is a thing which we can feed to seek, and it gives us back a sequence on its elements. So it will work for lists. If the list is non-empty, then it can be used as its own sequence, but that's kind of an implementation detail. Then we have vectors. We can ask for a sequence, and also for all the other data structures. And sometimes it depends. If the input is ordered, the output will also be ordered. But for example, on hash maps or hash sets, the order of the elements isn't determined up front. You get all the elements, but it's not known in which order. And the nice thing, we can also extend this to existing things like Java string. It can be also turned into a sequence of the contained characters. And there's something happens which is maybe confusing in the first place when you try to somehow get a grasp for sequences. When you feed a string to first, you get the first character. So does it make string a seq, because first is a sequence function? The answer is of course no, but all the sequence functions call seek implicitly on your behalf, so that we don't have to put everywhere seek where we want to use the sequence functions. It's a convenience, but it doesn't mean when you can feed a string to the sequence function that it means immediately that the string actually is the seq itself. So this was all based on existing data structures. You have some data structure and can derive a seq from the data structure, but we can also create completely new sequences on our own. For example, with generator functions. So iterate, f and x, gives us a lazy sequence with the first element to be x, the second element to be f of x, and the third element to be f of x, and so on. And when we remember our initial example with the numbers, we can simplify it by simply using this iterate function, and it will take care of doing all the lazy const stuff which we had to do manually before. Then we can simply repeat an element infinitely many times. We can have side effects. For example, reading from a file, you want to read lines from a reader. You have a function which reads from the stream, and you just say, call this function repeatedly, and every element will be the result of the call of such a function. And since it's based on side effects, you will get a new element. It could also be this example from yesterday from Stefan Tilkoff with the random numbers, the sequence of random numbers. And here again, we have this, since there are side effects in the game, we have to pay attention to the dynamic context. Take this example for reading lines from a reader, and when you pass this sequence out of the enclosing this open, and the reader gets closed before you realize the whole sequence, then you basically get an error. Then we can create new sequences based on existing sequences. And again, don't forget, this is a vector, it's not a sequence, but cycle calls seeks on our behalf, it's called seek on our behalf. So we can feed it directly into, and cycle will just go through all the elements of the data structure, of the input sequence, and when it's at the end, it just starts afresh, and you get an infinite cycle of the elements. Then, of course, we can concatenate sequences together, and again, if this, for example, numbers returns an infinite sequence, though the result of concat may also be infinite in this case. We can be picky about what we want to have. So we have all the numbers, and we may only want to have the even numbers. So we just filled out the odd ones. Or we may be forgetful about our data, so we dropped 2 elements on the floor and get a shortened sequence of the input. So, geese. Now I travel to London, and this guy just gives me a tutorial and sequences which I can read on the net. But these examples are not that innocent as one might think, especially not the last 2 ones, because they really exhibit a behavior which exhibit a problem in this whole setup that led to a historic cut, really through how we understand sequences and how they work in the code. And I think this cut left some scars till today. And the issue is that there are many ways of how you can be lazy, and lazy-cons chose one way, but it turned out that it's not sufficient for our purposes. Because lazy-cons returns something concrete. It returns a sequence, and at that moment you need either a first element or it's nil. You have to decide. And when you now call, for example, take this last example, drop, and you call drop 2 on a sequence which has only 1 element, you have to return nil. So there is no way in writing a lazy drop in this setup, because as soon as you have drop, you have to go in there and realize the input sequence to see whether there are enough elements to return a lazy cons again, or whether there the drop exhausts the input sequence and you basically get nil. So the solution to that was we delay even the creation of the sequence. And as you might, this is maybe something you already know. It's what we now know as the lazy-seq macro, and it basically takes a body which will produce a sequence. And again, there is some implicit seek in there that you can also provide a seekable, like a vector, as a body. And this will really only be created when you want the sequence, when you really realize the sequence. So, to do that, we just call seek on it, and we get back our usual sequence. So it's calling seek on the lazy-seq will realize it. And the sequence interface, which was at the beginning first and next. So next was called differently, but let's don't go there. So first and next were basically the functions you used on sequences. First gives you the first element in the sequence, and next gave you the tail sequence. And this is now extended with rest, which gives us the unrealized tail sequence. Basically, what we now get in the drop case, it's not the sequence anymore, but we get a promise that in the future we can calculate this drop when we require it, when we call seek on this resulting issue. So the changes were that there is now an empty sequence, because we don't know up front. Take, for example, lazy-seq nil. It would be the empty sequence, but we don't know, because to know we have to realize the sequence. Up to now, it's only a promise that we get something. So when we do seek on the sequence, it's not the identity anymore. In the beginning, we only had either nil or cons or lazy cons. And calling seek on it was just giving us back what we had. And this is now not the case anymore, because when we call lazy-seq on the when we call seek on the lazy-seq, the body is realized and we get basically the body sequence. And everything was promoted to a logical collection. This allows full laziness. So we can now write a filter which is fully lazy. We can, it had the same trouble, because for filter it has to check, is there some element in my input which satisfies the predicate? And we can write a fully lazy drop, and the price is, of course, nothing comes without a price tag. We don't have nil punning anymore. In the beginning, we could use the sequence in conditional statements. So it was either nil, which was false, or it was something which was not nil, or Boolean false, and then we knew, okay, there is something in there, and we can go on processing stuff. This is now gone, so we have to readjust a little bit how we think about this. And here I wander off a little bit into a minefield, because I don't quite understand why is this still a sequence. Why is lazy-seq still basically implementing first and next and rest? Because when we compare the two ways of calling things, we have lazy cons, which takes the first element and which takes the next element. And we have lazy-seq, which just takes something which will produce a seek. So it doesn't really take the elements we would expect. And my answer is maybe a little bit crazy, but I think that the lazy sequence actually isn't a sequence at all in the old definition, but it's a seekable, because I have to call seek on it to realize it. And this leads to a simple insight: always capture the return value of seek, because we cannot know just from the lazy-seq whether there is a first element, so we have to call seek on it anyway. And otherwise, if we call first on the lazy sequence and it gives us nil, what does that mean? We don't know. It could be that the lazy sequence is empty and there is no first element, or it could be a nil, which is just the element of the input sequence. So we have to check always with seek whether the lazy-seq is empty or not, and to do really computation which is also nil safe. Just a thought experiment. What does that lead to? Well, there's a question: what if map over a vector would return a vector? And there's always the question, then it's not lazy anymore and stuff like that. There are other languages which basically have this kind of polymorphism on the data structures for mapping over sequential things. And the answer is, does not have to be that case. It could be a special type of vector which is returned, which is based on the original vector. And as soon as you access an element, this computation is actually done to apply f to this element, and then the result is stored. So we basically delay the application of f until we access this element the first time. Could implement the vector interface. You can conjure it, you can do peek pop, stuff like that, and you would remain you would keep the attributes of the input sequence, in this case a vector. At the moment this is not possible because the sequence functions return iSeeks, which lazy-seq is also an I-seq, but it could be just a seekable and one of many ways which map could return. And for the map, the data structure, there is such an implementation which delays the actual computation of what you get from the element. So it's possible, but maybe not really feasible in reality. This is just a startup experiment, and you can call me maybe crazy chestnut that I think about this stuff in such a way. But it shows that there is still some discussion going on, and how these sequence functions could be improved to help doing stuff in a better way. And this leads us basically to the near future, so we are slowly catching up from the past and drifting off into the near future. And we come to people who know what they're doing and who also think about this stuff and do it the right way. The problem with sequences is, the advantage is we can do computations on the elements of a collection without knowing the input structure. It could be a vector, it could be set. Our functions don't have to care for that. But the downside is we get this sequential output structure, and we get the overhead of laziness if you maybe don't need it. And as we all know, there's recent development which is called reducers by Richicki. And this is, again, a new type of view on a collection. Now you get a reducible, which keeps knowledge about the original input. And then you have the reducers, which also act like the sequence functions on reducibles. So you can get the same way of structure-independent computation, but the information about the input structure is kept all through for your, so that you don't have to do it. The computation is really delayed until it's really required, so it's still lazy. And the downside is it's all or nothing. When you then go into reduce, you have to process the whole structure, which of course is then maybe faster because you can exploit. If I have a tree, I can split the subtrees on different CPUs, but you have to process the whole structure. Will this replace lazy-seq? No, probably not, because there are still infinite sequences and sequences which don't fit into memory. If you have this large data processing in mind, where you go through a huge file which does not fit in your memory and you go through there step by step, this won't be possible with reducers because they act on the data structure. It must be there, and the data structure is not lazy, it's realized in the memory. And then there are also maybe in non-all or nothing situations where you don't take where you take off elements from your input sequence, but don't want to compute everything, but maybe you want to stop at some point. So all in all, lazy-seq is here to stay. We will have it around for a while, and I'm looking forward to the near future, how future improvements of the language will happen. Questions? Yeah, the question was, how do chunk sequences fit into this picture? And it happened somewhere around here, where we had the change to lazy-seq. And the idea is to basically have, when you have, for example, a vector, which has underneath the hood arrays where the elements are stored, then you can say, okay, I don't transform it element by element by element, but in chunks, so that you can say, okay, I take this array and transform it at once, and then take the next chunk with the array and transform it at once. And this takes a little bit of the cost when we go here. The cost of the overhead of laziness. So in theory, it's a little bit faster than a pure sequence, but you get different effects that you get slightly ahead of time. So, okay.
No, keep answering. Okay. I'll do tidying up.
Does that answer your question?
Cool. Thank you again.
Good.